Gravity is the silent architect of our universe, but in the void, it breaks all the rules. Albert Einstein once said the most incomprehensible thing about the universe is that it is comprehensible. This journey will reveal 21 astonishing ways gravity defies our expectations, from black holes that trap light to a mysterious energy tearing the cosmos apart. By the end, you will see the universe through a completely new lens, understanding forces that rewrite the laws of physics. How can something invisible dictate the fate of galaxies? And what happens when time itself starts to bend? What if everything you know about gravity is just the surface of a much deeper mystery? How does it feel to realize the force that keeps your feet on the ground is also the greatest enigma in the cosmos? Galaxies spin with such ferocious speed that every star within them should be flung into the void. Yet they hold together, bound by an unseen hand. This is the first great defiance of gravity, the phantom force we call dark matter. Back in the 1930s, a brilliant and often contentious astronomer named Fritz Zwicky was studying a distant cluster of galaxies. He noticed something bizarre. The individual galaxies were moving so quickly that the cluster's own gravity, from all the visible stars and gas, should not have been enough to hold them. The entire system should have flown apart. Zwicky concluded there had to be something else there, a huge amount of mass he could not see. He called it Dunkel Materie, dark matter. For decades, his idea was largely ignored. Then, in the 1970s, astronomer Vera Rubin provided the stunning proof. By meticulously measuring the rotation speeds of stars within spiral galaxies, she found a puzzle that shattered conventional physics. According to Newton's laws, stars closer to the galactic center should orbit much faster than those on the outer edges, just as Mercury orbits the Sun far more quickly than Pluto. But Rubin's data showed something else entirely. The stars, whether near the center or far out in the galactic fringe, all moved at roughly the same speed. The only possible explanation was that each galaxy was embedded within a gigantic, invisible sphere of matter, a halo exerting a gravitational pull that kept the outer stars from drifting away. This unseen substance, this dark matter, does not absorb, reflect, or emit any light. It is completely transparent. We cannot see it, but we can see what it does. Its gravity is the cosmic glue that holds galaxies together and weaves the vast web of the universe itself, guiding where galaxies form and how they cluster. One of the most dramatic pieces of evidence came from a cosmic collision known as the bullet cluster. When two galaxy clusters slammed into each other, the clouds of normal matter, the hot gas, got stuck in the middle, slowed by the drag of a tremendous impact. But the dark matter, which does not interact with anything except through gravity, sailed right through the collision. By mapping the gravitational lensing, the way the cluster's gravity bent light from more distant galaxies, astronomers could pinpoint where the mass actually was. The result was a ghostly map showing that most of the mass was now separate from the normal matter. We were literally seeing the shadow of dark matter. So what is it made of? The leading candidates are particles with names like WIMP, or weakly interacting massive particles, theoretical entities that barely interact with normal matter. But despite decades of searching with incredibly sensitive detectors deep underground, we have not caught one yet. How does a component we cannot see dictate the structure of everything we can? This invisible scaffolding of the cosmos is the first astonishing clue that gravity is playing by a set of rules we are only beginning to read. But if dark matter is the invisible hand holding the cosmos together, what force could possibly be strong enough to tear it apart? The answer lies in the second astonishing defiance of gravity, the repulsive push of dark energy. For much of the 20th century, astronomers believed the universe's expansion, born from the Big Bang, was gradually slowing down. The collective gravitational pull of all the galaxies, all the stars, all the dark matter, was thought to be acting like a cosmic brake, gradually reining in that initial outward flight. Then, in the late 1990s, two independent teams of scientists made a discovery so shocking it would win them the Nobel Prize. By observing incredibly distant stellar explosions, a specific type of supernova that acts as a standard candle for measuring cosmic distances, they found that these beacons were fainter than expected. The universe was not slowing down, it was speeding up. The expansion of the cosmos was accelerating, as if some invisible, repulsive force was blowing the very fabric of space apart. This phantom force was named dark energy. It is now understood to make up a staggering 68% of the entire universe. Think about that for a moment. The stuff of planets, stars, and galaxies, everything we can see and touch and measure, accounts for less than 5% of reality. Dark energy is the dominant component of the cosmos, and it works in direct opposition to gravity's pull. This revelation was a homecoming for one of Einstein's oldest ideas, his cosmological constant. He had originally inserted this mathematical fudge factor into his equations of general relativity to force a static, unchanging universe, a concept that was the scientific consensus at the time. When Edwin Hubble later proved the universe was indeed expanding, Einstein famously discarded the constant, calling it his greatest blunder. But it turns out he may have been right for the wrong reason. The cosmological constant is now the leading explanation for dark energy, representing a constant energy density permeating the vacuum of space itself. This energy possesses a bizarre property, negative pressure. While gravity pulls matter together, this negative pressure exerts a kind of anti-gravitational push on the cosmos as a whole, stretching space and driving galaxies away from each other at ever-increasing speeds. We see its imprint everywhere, most clearly in the faint afterglow of the Big Bang, the cosmic microwave background. The precise patterns in this ancient light reveal a universe whose geometry is flat, a condition that requires dark energy's dominant presence. The ultimate consequence of this relentless push is a cold, lonely, and isolated fate for the cosmos, a scenario known as the Big Freeze. In this distant future, the acceleration will become so extreme that distant galaxies will be pushed beyond our horizon, their light forever lost to us. The observable universe will shrink to a mere handful of nearby galaxies, all else having vanished into an impenetrable void. Why would the universe be built with such a fundamental contradiction? A force that pulls woven into the same fabric as a force that pushes. This cosmic tension, the silent war between dark matter's grip and dark energy's push, defines the very fate of everything, and it sets the stage for an even more dramatic battlefield, where gravity does not just pull or push, but twists the very fabric of reality into impossible knots. The silent war between dark energy's push and dark matter's pull finds its ultimate expression in a place where gravity wins completely. A black hole is a puncture in the fabric of the cosmos, a point where the warping of spacetime becomes so severe that the known laws of physics break down. This extreme environment, predicted by Karl Schwarzschild's solutions to Einstein's equations, is our third astonishing defiance. At its heart lies the singularity, a point of infinite density where matter is crushed out of existence. Surrounding this point of no return is the event horizon, a one-way membrane in spacetime. Once anything, even light, crosses this boundary, it can never come back. It is the ultimate prison, built not from walls, but from gravity itself. But the true strangeness unfolds just outside this edge, where gravity is not yet absolute, but is already rewriting the rules of reality. Here, the curvature of spacetime becomes a tangible force. Imagine falling feet first toward a black hole. The gravitational pull on your feet would be immensely stronger than the pull on your head. You would be stretched into a long, thin stream of atoms, a process physicists call, with grim humor, spaghettification. Time itself becomes a fluid concept. A clock falling toward the event horizon would appear to tick slower and slower to a distant observer, an effect known as time dilation. To someone watching from a safe distance, you would seem to freeze in place, your image fading to red and then vanishing as you took, from their perspective, an infinite amount of time to cross the horizon. The first ever image of the black hole at the center of galaxy M87, captured by the Event Horizon Telescope, gave us a stunning visual of this warping. The glowing ring of hot gas is not the event horizon itself, but light bent into a perfect circle by the black hole's immense gravity. The dark shadow at its center is the closest we can come to seeing the unseeable, a silhouette of the event horizon. For rotating black holes known as Kerr black holes, the distortion is even more profound. They drag the very fabric of spacetime around with them, like a spinning spoon in a thick liquid. This creates a region outside the event horizon called the ergosphere, where nothing can stand still. Every bit of matter is forced to rotate with the black hole, a cosmic whirlpool from which energy can theoretically be extracted. Even light is not immune to this gravitational tyranny. Photons struggling to climb away from a black hole lose energy in the process, their wavelength stretching and shifting toward the red end of the spectrum. This gravitational redshift is a direct testament to the energy gravity steals from light itself. How can a force born from mass so thoroughly dismantle our fundamental experiences of space and time? This radical distortion is more than a cosmic curiosity. It is a violent laboratory, hinting that to truly understand gravity, we must peer into the quantum secrets that must be swirling at the very edge of existence. Einstein's equations did more than predict black holes. They whispered of waves, ripples surging through the very fabric of spacetime. In 2015, a century after his prediction, we finally learned to listen. This is the fourth astonishing defiance of gravity, the illusion of gravitational waves. Think of spacetime not as a static stage, but as a vast, flexible membrane like the surface of a pond. When something massive accelerates violently, it creates ripples in that membrane, distortions that travel outward at the speed of light. The most powerful sources are cosmic collisions, like two black holes spiraling into each other in a final, furious dance. As they merge, they shake the universe, sending tremors across a billion light years. Detecting these whispers required one of the most sensitive experiments ever built, LIGO, the Laser Interferometer Gravitational Wave Observatory. Conceived by visionaries like Rainer Weiss, LIGO uses laser beams traveling down 4-kilometer-long arms arranged in an L shape. A passing gravitational wave subtly stretches one arm while squeezing the other, changing the distance the lasers travel by an amount tinier than the width of a proton. This infinitesimal shift creates an interference pattern that betrays the wave's passage. The first direct detection on September 14, 2015, was the sound of two black holes, each about 30 times the mass of our Sun, colliding. We did not see it. We heard it, a distinctive chirp that rose in frequency and amplitude before ending abruptly, the signature of a final merger. This was not just a confirmation of Einstein's genius, it was the birth of an entirely new sense for astronomy. We are no longer limited to observing the universe through light alone. Now we can feel its vibrations. A landmark event in 2017, known as GW 170817, demonstrated the power of this new sense. This time, the waves came from the collision of two neutron stars, the ultra-dense corpses of dead suns. Crucially, traditional telescopes detected the flash of gamma rays, light, and other electromagnetic signals from the same event. This multi-messenger approach allowed astronomers to pinpoint the galaxy where it happened and study the aftermath in incredible detail, watching the forge where heavy elements like gold and platinum are created. What can these space-time vibrations, these echoes of cosmic violence, teach us? They are pristine messengers, carrying information about their sources almost completely unaffected by the matter they pass through. They allow us to test general relativity in the most extreme gravitational fields, and to census the invisible population of black holes drifting through the cosmos. Every chirp and rumble is a story, a direct report from the most energetic events since the Big Bang. These ripples do not just travel through space, they carry us back toward the very beginning, to the moment the cosmos itself was born in an unimaginable surge of expansion. Those ripples in spacetime carry us back toward the very beginning, to a moment of creation so violent it challenges our grasp of reality. In its first fleeting instance, the universe performed its most audacious trick. Gravity, the force of attraction, somehow became a force of repulsion, driving an expansion so swift it outpaced the speed of light itself. This is the cosmic inflation paradox, the fifth astonishing way gravity defies all expectation. The theory, pioneered by physicist Alan Guth in the 1980s, proposes that a minuscule fraction of a second after the Big Bang, the cosmos underwent a breathtaking growth spurt, doubling in size again and again in an unimaginably short burst. This exponential inflation took a subatomic speck of space and stretched it to a scale larger than our entire observable universe in less than a blink of an eye. What could possibly power such an event? The answer lies in a hypothetical energy field, a sort of cosmic engine that filled the vacuum of space. This field possessed a bizarre property, a negative pressure that, according to the equations of general relativity, generates a repulsive form of gravity. For that fleeting moment, gravity did not pull things together. It blew them apart with ferocious intensity. This sudden, violent stretching solved some of the cosmos's deepest puzzles in one elegant stroke. Consider the horizon problem. When we look at the cosmic microwave background, the oldest light in the universe, we see that regions on opposite sides of the sky have the exact same temperature. But according to the old Big Bang model, these regions were never close enough to exchange heat or information, their light only reaching each other now. How did they achieve such perfect thermal harmony? Inflation provides the answer. Before the rapid expansion, all these distant patches were intimately connected, a tiny, cozy region in thermal equilibrium. Inflation then stretched this unified space to cosmic proportions, locking that uniform temperature across the vast sky we see today. This process also explains why the universe appears so remarkably flat. Just as inflating a balloon smooths out its wrinkles, the inflationary burst stretched the fabric of space to incredible smoothness, resulting in the nearly flat geometry we measure today. But inflation did more than just smooth and stretch. It also planted the seeds for all future structure. Quantum fluctuations, tiny, random jitters in that primordial energy field, were stretched to astronomical sizes by the rapid expansion. These minute ripples in density became the gravitational blueprints for everything, the slight overdensities where dark matter would later gather, pulling in gas to form the first galaxies, stars, and eventually us. Our entire cosmic web was born from microscopic quantum seeds magnified by inflation. The theory even opens a dizzying door to the multiverse, a concept further developed by physicists like Andre Linde. If inflation can start, perhaps it never truly stops everywhere, giving rise to countless bubble universes, each with its own unique laws of physics, within an ever-expanding cosmic foam. The hunt for direct proof of inflation continues. Experiments like BICEP scan the cosmic microwave background for a specific pattern, a curled polarization in the ancient light called B modes, which would be the unmistakable imprint of primordial gravitational waves, the tremors from inflation's explosive birth. How could the force that builds galaxies have once been the very engine that blew the universe apart? This early repulsion lies at the heart of gravity's deepest contradiction, a force of both creation and destruction. whose first act was to set the stage for everything that followed by momentarily breaking its own most fundamental rule. These cosmic voids are not just empty space. They are active players in the gravitational story, vast deserts of near-nothingness that warp the behavior of the cosmos itself. Picture a region of space so empty it could span hundreds of millions of light years, containing only a handful of lonely galaxies where there should be thousands. This is the Boötes void, a cosmic cavern of staggering proportions. Within these immense underdensities, the rules of gravity shift in a subtle but profound way. With so little matter to provide a gravitational pull, the relentless push of dark energy finds less resistance. The expansion of space itself can actually run faster inside these voids compared to the denser walls of the cosmic web. This local variation in the expansion rate is not just a curiosity. It may hold the key to one of the biggest puzzles in modern cosmology, the Hubble tension. This is the troubling discrepancy between measurements of how fast the universe is expanding today. One method, using the cosmic microwave background, gives one value. Another, using supernova and other local markers, gives a slightly faster value. The difference is small but persistent, suggesting a potential flaw in our standard model. Astronomers like Laura Mersini-Houghton have theorized that these cosmic voids could be the source of the tension. What if we, our entire local group of galaxies, are sitting inside one of these underdensities, a place now known as the KBC void? From our vantage point inside this bubble of relative emptiness, our measurements of the local expansion rate would be slightly skewed, appearing faster than the true global average because dark energy's push is less contested here. We would be like sailors in a calm lagoon, misjudging the strength of the ocean's current beyond our sheltered waters. Mapping these voids is a monumental task achieved through massive redshift surveys, which chart the three-dimensional positions of millions of galaxies. These maps reveal the true architecture of the cosmos, a sponge-like structure of dense filaments and walls surrounding these enormous, dark bubbles. The gravitational influence of a void is counterintuitive. It is not that the void itself pulls things in. Rather, the immense walls of matter surrounding the void exert a stronger gravitational pull on the galaxies near its edge, effectively pushing them away from the empty center. It is the gravitational pull of the surrounding cosmos that defines the void's influence, sculpting its boundaries and influencing the motion of every galaxy on its fringe. Why should emptiness hold such sway? These great cosmic deserts remind us that gravity is not just about what is there, but profoundly about what is not. The absence of matter creates a gravitational landscape as varied and influential as its presence, a shadowy topography that guides the flow of galaxies and may even be distorting our most fundamental measurements of cosmic fate. This emptiness sets the stage for one of gravity's most beautiful and useful illusions, a trick of light that allows us to see the invisible. This bending of light is not a flaw in the cosmos, but a feature, a spectacular illusion sculpted by gravity itself. The seventh astonishing defiance is the mirage of gravitational lensing, where the universe uses its own mass as a lens, twisting light into arcs, rings, and multiple images. It is a direct and beautiful validation of Einstein's general relativity, proving that mass tells spacetime how to curve, and that curved spacetime tells light how to move. The first dramatic confirmation came during the total solar eclipse of 1919. Sir Arthur Eddington led an expedition to photograph the stars appearing near the sun's obscured rim. Their positions were slightly shifted, their light bent by the sun's gravitational field, just as Einstein's equations had predicted. This was the moment Einstein became a global celebrity, his theory moving from abstract mathematics to observable fact. Today, we see this phenomenon on a colossal scale. When a massive object, like a galaxy cluster, sits between us and a more distant galaxy, It acts as a natural telescope. The cluster's immense gravity warps the fabric of spacetime around it, creating a lens that distorts and magnifies the light from the background source. Astronomers like Joachim Wambsgans have pioneered the use of this effect to map the invisible. The precise way the light is bent reveals the total mass of the lensing cluster, including the vast halos of dark matter that would otherwise remain completely hidden. We are literally using light to weigh the dark. The effects of lensing come in different strengths, each revealing a different part of the cosmic story. Strong lensing is the most dramatic, where the alignment is so perfect that we see multiple images of the same distant quasar or brilliant arcs of light encircling the foreground cluster, like a cosmic halo. The Einstein cross is a famous example, a single quasar whose light is split into 4 distinct images by the gravity of an intervening galaxy. Weak lensing is more subtle but just as important. It does not create multiple images, but instead stretches the shapes of thousands of distant galaxies in a coherent way, like looking through a room full of faint, warped windows. By statistically analyzing these tiny distortions, we can create vast maps of the dark matter web that permeates the universe. Then there is microlensing, a temporary brightening of a distant star that occurs when a dark, compact object, like a solitary planet or a dim star, passes directly in front of it. The object's gravity acts as a tiny lens, focusing the star's light for a brief period, sometimes just days or hours. This method has become a powerful tool for finding rogue exoplanets that drift, unattached to any star, through the interstellar darkness. Perhaps the most profound application of lensing has been in the Hubble Space Telescope's Frontier Fields program. By using massive galaxy clusters as natural magnifying glasses, Hubble peered deeper into the universe than ever before, observing some of the earliest and faintest galaxies ever seen, their light amplified by this gravitational trick. How does gravity turn the universe into a natural telescope? It reveals that the cosmos is not a static stage, but a dynamic, malleable medium where light does not always travel in a straight line. This beautiful illusion, however, hints at a deeper conflict. For gravity to bend light so perfectly, it treats light as a wave riding the curves of spacetime. But what happens when we look at the smallest scales, where light behaves as a stream of individual particles? This bending of light foreshadows a fundamental clash, a point where the smooth geometry of Einstein's universe collides with the frantic, probabilistic world of the quantum. That beautiful cosmic mirage, born from gravity-bending light, reveals a universe far more fluid than we ever imagined. But this flexibility extends beyond the paths light takes, reaching into the very flow of time. The 8th astonishing defiance is gravitational time dilation, the profound reality that gravity does not just warp space, it warps time itself. A clock ticks slower in the presence of a strong gravitational field. This is not science fiction, it is a fundamental prediction of Einstein's general relativity, confirmed by countless experiments. The principle behind it is the equivalence principle, a cornerstone of Einstein's thinking. He realized there is no difference between being in a stationary room on Earth and being in a rocket accelerating through empty space at 9.8 meters per second squared. In both cases, you feel your weight. This equivalence between gravity and acceleration led him to a stunning conclusion. If time slows down for someone moving at high speed, a consequence of his earlier theory of special relativity, then time must also slow down for someone in a powerful gravitational field. Gravity, in essence, is indistinguishable from acceleration, and both put the brakes on time. We rely on this corrected time every single day. The Global Positioning System, a network of satellites orbiting Earth, is a practical application of relativity in your pocket. The satellites are farther from Earth's gravitational pull, so their onboard clocks actually run faster than identical clocks on the ground. If engineers did not deliberately program this time difference into the system, your GPS location would be off by several miles within just a few hours. The universe itself provides more extreme tests. In the 1960s, physicists Robert Pound and Glenn Ribka performed a classic experiment. They fired a beam of gamma rays down a tower at Harvard University. As the rays fell downward, gaining energy in Earth's gravitational field, their frequency very slightly increased. This tiny shift, exactly matching Einstein's prediction, proved that gravity steals energy from light, and in doing so, alters its perception of time. An even more famous demonstration was the Hayfel-Keating experiment in 1971. Scientists flew extremely precise atomic clocks on commercial airliners around the world. When these traveling clocks were compared to stationary ones back on Earth, they showed a measurable time difference. The combination of their speed and their altitude, a slightly weaker gravity, had caused them to run at a different rate. The effect was tiny, mere billionths of a second, but it was undeniably real. Now, consider the ultimate extreme. Near the event horizon of a black hole, where gravity is almost infinitely strong, time dilation becomes absolute. To a distant observer, a clock falling toward the black hole would appear to tick slower and slower, eventually freezing completely at the moment it crosses the horizon. From our perspective, time at that edge has effectively stopped. What does this mean for the nature of reality? It shatters the Newtonian idea of a universal, ticking clock for the cosmos. There is no single now that applies everywhere. Your now and the now of someone near a black hole are not the same. Time is not a rigid backdrop. It is a malleable, personal experience, shaped and stretched by the gravitational landscape you inhabit. This temporal twist, this intimate link between gravity and time, pushes our understanding to a breathtaking frontier. It suggests that the information about a three-dimensional volume of space might be entirely encoded on its two-dimensional boundary, like a cosmic hologram. If gravity can so profoundly dictate the passage of time, could it be that time itself is not a fundamental entity, but an emergent property, a story written by gravity itself? This holographic possibility is a radical step, one that leads us to question the very nature of information and where it truly resides. That holographic idea, where information paints the very fabric of reality, leads to a conceptual leap that redefines gravity itself. The ninth astonishing defiance is the holographic principle, a theory suggesting that gravity is not a fundamental force, but an emergent illusion, a side effect of information processing on a cosmic scale. Proposed by physicists Gerard T. Hooft and Leonard Susskind, this radical idea was born from the fiery paradox of black holes. A black hole's entropy, a measure of its information content, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon. This was the first profound clue that all the information needed to describe the three-dimensional interior of a black hole might be perfectly encoded on its two-dimensional boundary, like a hologram on a flat plate that creates the illusion of a full three-dimensional image. The principle was then solidified into a powerful mathematical framework by Juan Maldacena through what is known as the AD-S/CFT correspondence. This work showed a precise duality, a kind of cosmic dictionary. On one side, you have a universe with gravity, described by string theory in a warped space called anti-de Sitter space. On the other side, you have a description of a universe without gravity, a quantum field theory that lives on the boundary of that space. These two seemingly different worlds are mathematically equivalent. They are two descriptions of the same reality. This implies that gravity, as we experience it in the bulk of space, is not a fundamental ingredient. It emerges from the complex quantum interactions and, crucially, the quantum entanglement of countless microscopic degrees of freedom living on the lower dimensional boundary. This perspective offers a stunningly elegant solution to the black hole information paradox. The paradox asks what happens to the information that falls into a black hole. If it is truly lost, it violates a core tenet of quantum mechanics. But if the black hole is a hologram, the information is never lost inside. It remains smeared and stored on the event horizon, and it is eventually radiated back out, scrambled but preserved, as the black hole slowly evaporates via Hawking radiation. The very fabric of spacetime and the gravity that comes with it may be woven from the threads of quantum entanglement. This is not just abstract theory. The way entanglement entropy behaves in these systems directly supports the idea that connectivity in space is created by quantum links. So what does this mean for our universe? Could the force that anchors us to the Earth, that guides the planets, simply be a collective mirage? A statistical consequence of the universe processing an unimaginable amount of information. This conceptual leap even finds a curious echo in the tiny anomalies of planetary motion, the small deviations in orbits that once led to the discovery of Neptune. Perhaps future refinements of gravity will not come from adding new particles, but from understanding the cosmic code from which gravity itself emerges. That cosmic code, emerging from the boundary of reality, finds one of its earliest and most elegant validations much closer to home, in the silent, persistent dance of the innermost planet. Mercury's orbit has long been a celestial whisper of something deeper at work. It traces not a perfect, repeating ellipse, but a delicate rosette pattern, its point of closest approach to the Sun slowly shifting over time. For centuries, this drift, known as precession, presented a nagging puzzle. The gravitational tug of other planets explained most of it, but a tiny sliver remained stubbornly unaccounted for, a discrepancy of about 43 arcseconds per century. To put that in perspective, it is the angular width of a human hair seen from a mile away. Yet this minuscule anomaly was a crack in the foundation of Newtonian gravity. Astronomers like Simon Newcomb meticulously documented this leftover drift, fueling speculation about a hidden planet, dubbed Vulcan, orbiting inside Mercury's path. But no such planet was ever found. The answer was not a missing world, but a new understanding of space and time. When Albert Einstein completed his theory of general relativity in 1915, he turned to this very problem. His equations showed that the Sun's mass warps the spacetime around it, and Mercury, moving so swiftly through this curved environment, follows the resulting geodesic. It is not being pulled by a force, but simply following the shortest path through a warped landscape. The planet's orbit itself rotates because the geometry of space near the Sun is not static. It is a swirling, dynamic fabric. Einstein later wrote that seeing this calculation match the observed anomaly gave him heart palpitations. The thrill of knowing his theory had captured a fundamental truth of the cosmos. This was the first solid proof that gravity is geometry. Modern missions have verified this with astonishing precision. NASA, a messenger spacecraft, which orbited Mercury for years, used laser ranging to track the planet's motion, confirming Einstein's prediction to within a fraction of a percent. We now see this effect, though far smaller, in the orbits of other bodies, including Earth itself, and even in the dance of distant pulsars. How can a tiny orbital quirk, a wobble smaller than a minute of arc, reveal the true nature of the universe? It demonstrates that gravity's influence is not a simple, instantaneous pull, but a complex dance dictated by the shape of reality itself. This precise choreography, however, begins to falter when we look beyond our solar backyard, where the rules of gravity seem to change on a galactic scale. Mercury's perfect rosette orbit, explained by Einstein, reveals a universe governed by elegant geometry. Yet when we zoom out to the scale of entire galaxies, that beautiful predictability shatters. Spiral galaxies like our own Milky Way spin with a rhythm that defies all classical logic. According to Kepler's laws, Stars on the outer fringes should orbit much slower than those near the bright core, just as Pluto crawls compared to Mercury. But they do not. Stars far out in the galactic hinterlands race along at nearly the same speed as their inner cousins. This is the 11th astonishing defiance, the flat rotation curve, a ghostly signature written in starlight that points to a universe filled with unseen mass. The discovery of this anomaly is a story of meticulous observation. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford began measuring the velocities of stars in the Andromeda galaxy. They used the Doppler shift, the same effect that changes the pitch of a passing siren. By analyzing how the light from stars was stretched or compressed, they could calculate their speed. The results were unequivocal and shocking. The rotation curve, a graph of orbital speed against distance from the center, did not fall away as expected. It remained stubbornly flat, far out into the darkness where visible stars grew sparse. This could mean only one thing. A tremendous amount of invisible matter, a dark halo, must be enveloping each galaxy, its gravitational grip keeping the outer stars from flying off into the void. The visible galaxy, all the stars and gas we can see, was just the bright tip of a much larger, darker iceberg. This finding forced a profound choice upon physics. Either the universe contains about 5 times more matter than we can see, or our understanding of gravity itself is wrong on galactic scales. Some physicists, like Mordechai Milgrom, championed the second path. He proposed a modification to Newtonian dynamics, known as MND. This theory suggests that gravity behaves differently at the extremely low accelerations experienced in the outskirts of galaxies, eliminating the need for dark matter. For certain isolated galaxies, MND predictions can be surprisingly accurate. Yet the dark matter hypothesis has proven more resilient, especially when confronted with the full tapestry of evidence. The way galaxy clusters bend light through gravitational lensing, for example, reveals huge concentrations of mass that MND struggles to fully explain without some form of dark matter. The bullet cluster, where dark matter and normal matter were physically separated in a cosmic collision, presents a particularly stark challenge. Why do galaxies choose to spin in this impossible way? This galactic puzzle is not just a curiosity. It is the fundamental reason our universe looks the way it does. Without this unseen gravitational scaffolding, galaxies would never have formed in the early universe, and those that did would have quickly unraveled. The flat rotation curve is the direct observation of dark matter's hand at work, the force that gathered primordial hydrogen into vast structures and provided the stable orbits necessary for stars and planets to form. It is the silent, steady rhythm that maintains cosmic order, a rhythm played on strings we cannot see, hinting that the true composition of the cosmos is a mystery far deeper than light alone can reveal. That ghostly scaffolding of dark matter does more than hold galaxies together. It builds colossal rivers in the void, pulling entire galactic families on a journey toward an unseen destination. Our own Milky Way is not adrift, but racing at over 600 kilometers per second toward a mysterious, hidden concentration of mass known as the Great Attractor. This gravitational anomaly, lurking in the constellation Centaurus, represents the 12th astonishing defiance, revealing that gravity's pull operates on scales so vast they redefine our cosmic address. Discovered in the 1980s through large surveys of galaxy redshifts, the Great Attractor is a massive overdensity, a gravitational sink in intergalactic space. The challenge was that it lay directly behind the plane of our own Milky Way, hidden by thick clouds of gas and dust, a region astronomers call the zone of avoidance. Pioneers like Alan Dressler turned to infrared and radio telescopes, wavelengths that can pierce this cosmic veil, to finally glimpse the colossal structure pulling us in. They found not just one giant cluster, but a dense knot of galaxies and dark matter, a gravitational heart for our entire local motion. This discovery forced us to redraw the map of our cosmic neighborhood. We now understand that the Great Attractor is the central gravitational anchor of an immense structure called the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is a web of 100,000 galaxies all flowing together in a slow, cosmic river toward this common center. Our local group, including the Milky Way and Andromeda, is just one tributary in this vast flow. The gravity from this immense concentration creates a bulk flow, a coordinated movement of thousands of galaxies across hundreds of millions of light years. We can even see the imprint of this motion in the oldest light in the universe, the cosmic microwave background. This relic glow is not perfectly uniform. It appears very slightly warmer in the direction we are moving toward, and cooler in the direction we are fleeing, a phenomenon known as the dipole anisotropy. This temperature difference is our own motion painted onto the canvas of the Big Bang, a direct result of being pulled by the Great Attractor and other massive structures. But the story does not end there. Our entire Laniakea supercluster, with the Great Attractor at its core, is itself being pulled towards something even larger and more distant, the Shapley supercluster. This immense conglomeration of matter is the richest cluster of galaxies in our cosmic vicinity, a gravitational titan whose influence stretches across the observable universe. Ongoing projects with powerful new telescopes like the Square Kilometre Array, or SKA, are now mapping these cosmic currents in unprecedented detail, tracing the distribution of dark matter by observing the galaxies it steers. What hidden architecture of mass, woven from dark matter we cannot see, dictates the motion of galaxies on these grand scales? This relentless pull toward the unknown is not a chaotic tug of war, but a structured flow, a slow drainage of galaxies into the deepest gravitational wells. It reveals gravity as the great sculptor of the cosmos on the largest canvases, patiently gathering matter over billions of years, guiding the evolution of the universe itself through its silent, unwavering pull. This fundamental clash between the smooth and the grainy is the 13th astonishing defiance, the quantum gravity conundrum. For nearly a century, physics has been split between two incredibly successful but fundamentally incompatible descriptions of reality. On one hand, Einstein's general relativity paints gravity as the elegant curvature of a smooth, continuous spacetime. On the other, quantum mechanics describes a frantic, probabilistic world where fields and particles are inherently jumpy and uncertain. These two theories work perfectly within their own domains, but they fail catastrophically when forced to meet. The center of a black hole and the very first moment of the Big Bang are places where gravity becomes so intense and volumes become so tiny that the smooth fabric of spacetime should be replaced by a seething quantum foam. Here, the classical equations of relativity break down, spitting out infinities at the singularity. A theory of quantum gravity is the holy grail needed to describe these extreme frontiers, to understand what truly happens when spacetime itself is taken apart at the seams. The leading contenders offer wildly different visions of this underlying reality. String theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrations of these strings give rise to all the particles and forces we see, with one particular vibration corresponding to the graviton, the hypothetical quantum particle of gravity. This theory requires extra dimensions of space, curled up into sizes too small for us to perceive. In this view, gravity appears weak because it is diluted, leaking into these other dimensions. Loop quantum gravity takes a different path. Pioneered by physicists like Carlo Rovelli, it suggests that spacetime itself is not continuous, but is woven from a network of finite, discrete loops. Picture the fabric of reality not as a smooth sheet, but as a weave of a billion tiny threads. This quantized structure prevents the formation of true singularities, replacing the infinite density of a black hole with a hyper-dense, but finite, core that the theory calls a Planck star. These approaches also tackle profound conceptual problems like the nature of time. In quantum cosmology, time as we experience it may not be a fundamental feature. The universe's wave function might describe a static reality where the flow of time is an emergent illusion, a story that unfolds from the correlations between quantum events. How can a force that feels so continuous and geometric be built from discrete, quantized pieces? We are testing these mind-bending ideas by looking for their subtle signatures. The faint afterglow of the Big Bang might contain imprints from the primordial quantum fluctuations of spacetime itself. The final evaporation of black holes through Hawking radiation could reveal information about the quantum structure of the event horizon. This great unification is more than an academic exercise. It seeks to answer the most basic questions of existence, revealing what happened at the absolute beginning and what lies at the heart of darkness. This search for a unified theory inevitably draws us back to the cosmos, to a place where gravity's dominion is absolute, and its effects on light are pushed to the breaking point. Light itself pays a toll to escape gravity's grasp. A photon struggling to climb away from a massive object loses energy in the process, and since a photon's energy is tied to its color, this loss stretches its wavelength, shifting it toward the red end of the spectrum. This is gravitational redshift, the 14th astonishing defiance, a direct and beautiful confirmation that gravity steals energy from light. The principle was first tested in a landmark 1960 experiment by physicists Robert Pound and Glenn Ribka. They fired a beam of gamma rays down a tower at Harvard University. As the rays fell downward, they gained a tiny amount of energy in Earth's gravitational field, and their frequency increased by a minuscule but measurable amount, exactly as Einstein's equations predicted. This happens because of the intimate link between gravity and time. A clock deeper in a gravitational well ticks slower. From the perspective of someone higher up, the light emitted from below appears to have a lower frequency, because each crest of the light wave takes longer to arrive. It is the same phenomenon that makes a siren sound lower-pitched as it moves away. But here the cause is not motion, but the warping of time itself by gravity. We see this effect amplified across the cosmos. On the surface of a white dwarf, the dense corpse of a star like our Sun, gravity is so intense that light is noticeably reddened. Measurements of the redshift from Sirius B, the white dwarf companion to the brightest star in our sky, allowed astronomers to confirm its incredible density, with a mass comparable to the Sun packed into a volume no larger than Earth. On neutron stars, where gravity is billions of times stronger than on Earth, the redshift becomes so extreme that it significantly alters the appearance of any light struggling to escape its surface. This spectral shift is not just a stellar curiosity, it is a fundamental tool for cosmology. The Sachs-Wolfe effect describes how the cosmic microwave background, the oldest light in the universe, is subtly reddened or blue-shifted as it climbs out of the gravitational hills and valleys created by the early clumping of dark matter. These tiny temperature variations in the primordial glow are a fossil map of the universe's original gravitational landscape. Even within our solar system, the precise timing of signals from satellites must account for this effect, or our GPS systems would fail. What does this change in light's color reveal about gravity's energy cost? It shows that gravity is not a free force. It demands a payment of energy, a tax paid in the very color of starlight, forcing light to sacrifice its vibrancy to journey across the curved universe. This draining of energy from light even plays a subtle role in sculpting the delicate dynamics of planetary rings, where the collective gravity of a planet and its moons, each with their own redshift influence, helps shepherd countless particles into their precise orbital bands. Gravity's delicate touch reveals itself not only in grand galactic rivers, but in the intricate patterns adorning a planet's edge. Orbiting within the rings of Saturn, tiny moons perform a cosmic ballet, using their subtle gravitational pull to sculpt and confine countless particles. These are the shepherd moons, the 15th astonishing defiance, where minuscule tugs impose perfect order on a sea of chaos. The Voyager probes first revealed this phenomenon, discovering moons like Pandora and Prometheus orbiting on either side of Saturn's narrow F ring. Their gravity acts like a gentle but persistent fence, nudging stray ring particles back into the flock. An outer moon like Pandora, moving slightly slower, will exert a drag on particles, causing them to lose energy and fall inward. Conversely, an inner moon like Prometheus, orbiting faster, gives particles a gravitational kick, boosting their energy and pushing them outward. Together, they maintain the ring's impossibly sharp edges against the natural tendency to spread and diffuse. This dance is governed by orbital resonances, a celestial rhythm that occurs when the orbital periods of two bodies lock into a simple integer ratio. When a ring particle orbits, say, 3 times for every single orbit of a moon, their gravitational interactions repeat at the same point in space, amplifying over time. These resonances can be stabilizing, creating beautiful, undulating waves within the rings, or they can be destructive, clearing out entire gaps. We see this same principle at work far beyond Saturn. In the asteroid belt between Mars and Jupiter, the Kirkwood gaps are vast, empty regions where no asteroid can maintain a stable orbit, all because their orbital periods would resonate powerfully with Jupiter's gravity, which would inevitably fling them away. Resonances also generate immense internal heat through tidal forces. Jupiter's moon Io is the most volcanically active world in the solar system, its interior constantly kneaded and heated by a gravitational tug of war between Jupiter and its sister moons. How can such faint gravitational whispers carve such precise structures from cosmic debris? This ordered dance is a fundamental creative process. The same physics that sculpts a planet's rings also operates in the vast clouds of gas and dust where new solar systems are born. There, gravity's resonances can shepherd material, trigger the collapse of protoplanetary disks, and guide the formation of planets themselves, proving that the same delicate touch that braids a ring can also build a world. Gravity's delicate touch in sculpting planetary rings is the same force that, on a grander scale, forges the stars themselves. Deep within a vast, cold cloud of molecular gas, a silent drama begins as gravity overwhelms the outward push of internal pressure. This is the 16th astonishing defiance, the gravitational collapse that births stars, a process where creation and destruction are separated by the finest of balances. The initial trigger is known as the gene's instability, a criterion that dictates when a cloud's self-gravity becomes strong enough to make it collapse. Yet this collapse is never a simple, straightforward crush. The cloud is a chaotic place, filled with internal turbulence and, crucially, rotation. As the cloud contracts, it spins faster, just like a figure skater pulling in their arms. This conservation of angular momentum would normally fling the material apart, preventing a star from ever forming. But gravity finds a way, often spinning the infalling gas into a vast, flattened disk that orbits the nascent protostar at the center, a disk where planets may one day coalesce. Adding to the complexity are powerful magnetic fields, weaving through the cloud like cosmic threads, providing additional support and channeling the flow of material in jets that shoot out from the poles. We can witness this beautiful chaos in stellar nurseries like the Orion Nebula, where the Hubble and James Webb Space Telescopes have captured stunning vistas of glowing gas and dark, dusty disks, each one a potential solar system in the making. The final fate of a collapsing star is a cosmic weigh-in. determined by limits calculated by visionary astrophysicists like Subramanian Chandrasekhar. For a star like our Sun, the collapse is halted when the core becomes hot and dense enough to ignite nuclear fusion, the steady burning that defines a main sequence star. But for more massive stars, the endgame is far more violent. If the stellar core remaining after a supernova exceeds about 1.4 times the mass of our Sun, the Chandrasekhar limit, even the pressure of electrons pushing back against gravity, known as electron degeneracy pressure, will fail. The collapse continues, crushing protons and electrons together to form neutrons. For a brief moment, the unimaginable density of a neutron star, where a sun's worth of mass is packed into a city-sized sphere, can halt gravity's march. But push the mass even higher, past the Tolman-Oppenheimer-Volkoff limit, and nothing in the universe can stand in gravity's way. The collapse becomes total, space-time twisting inward upon itself to form a black hole. Why does this same force of collapse lead to both the gentle glow of a new star and the absolute darkness of a singularity? It is a matter of mass and the delicate interplay of opposing forces, where gravity's creative power to gather matter is matched only by its destructive potential to crush it out of existence. This explosive potential, where gravity's collapse triggers a titanic rebound, is one of the universe's most spectacular events. That same crushing force of gravitational collapse contains the seeds of its own spectacular reversal. A massive star lives for millions of years in a delicate balance, its outward push of nuclear fusion holding gravity's persistent pull at bay. But when its core finally fuses into iron, fusion stops generating energy. The balance shatters and gravity wins in a matter of seconds. The star's heart, an iron sphere the size of Earth but containing more mass than our Sun, collapses inward at a quarter the speed of light. This is the implosion that ignites the supernova explosion, a paradoxical event where gravity's ultimate victory triggers its own stunning defeat. The core crushes itself until it reaches the density of an atomic nucleus. Here, a bizarre quantum law takes over. Neutrons, forced into intimate proximity, simply refuse to be compressed any further. This neutron degeneracy pressure slams on the brakes, causing the collapsing core to bounce. A rebounding shockwave, a colossal sonic boom, is launched back out into the infalling star. For decades, computer simulations showed this shockwave stalling, unable to tear the star apart. The missing ingredient, theorized by physicists like Hans Bethe, was the ghostly neutrino. In the hellish conditions of the newborn neutron star, trillions of these nearly massless particles are created, carrying away immense energy. A fraction of them deposit their energy just behind the stalled shock, reheating it and turbocharging the blast until it rips the entire star to shreds. The supernova becomes a cosmic bomb, triggered by gravity but detonated by neutrinos. We witnessed this mechanism in action with supernova 1987A, a blast of light in a nearby galaxy. Hours before the visible explosion, detectors on Earth recorded a pulse of neutrinos, the direct signal from the core's implosion, a silent herald of the violent rebirth to come. The aftermath is a forge of creation. The cataclysm fuses elements far heavier than iron, from the silver in jewelry to the iodine in our bodies, and blasts them across interstellar space. The Crab Nebula, the expanding remnant of a supernova observed in 1054, is a continuing testament to this process, a cloud still pregnant with the raw materials for new stars, planets, and life. How can the force that extinguishes a star also be the very reason we exist? Gravity's destructive power in a supernova is the universe's primary engine of chemical enrichment, transforming simple atoms into the complex ingredients of worlds. This explosive release, however, leaves behind a relic where gravity is compressed into its most extreme stable form. That remnant of a supernova, a neutron star, is a cosmic atomic nucleus the size of a city. This is the 18th astonishing defiance of gravity, a place where the force of collapse meets its ultimate, stable match in the neutron star equation of state. Here, gravity has crushed matter to an almost unimaginable density, where a single teaspoonful would weigh billions of tons on Earth. The entire mass of our Sun, and more, is squeezed into a sphere no wider than Manhattan. This creates an environment so extreme that the very nature of nuclear matter is tested. The star is a colossal atomic nucleus, held together not by chemical bonds, but by pure gravity balanced against a bizarre quantum force, neutron degeneracy pressure. This is the pressure that arises when neutrons are packed so tightly together that they simply cannot be compressed any further. A last-ditch stand against total gravitational collapse. The precise way this pressure responds to density is what physicists call the equation of state. It is this single, fundamental property that determines whether a neutron star is relatively soft and large, or hard and small. This balance is incredibly delicate. If the accumulating mass pushes the core past a critical threshold, the Tolman-Oppenheimer-Volkoff limit, even neutron degeneracy pressure will fail. The collapse becomes unstoppable, and a black hole is born. We have learned much of this from the cosmic lighthouses known as pulsars. Their discovery by Jocelyn Bell Burnell in 1967 was a monumental accident that revealed these spinning neutron stars, their powerful magnetic fields funneling radiation into beams that sweep across space like a lighthouse. The incredible regularity of their pulses makes them superb natural clocks. The slow, precise changes in the timing of these pulses can reveal the subtle influence of gravitational waves. The most famous example is the Hulse-Taylor binary pulsar, two neutron stars orbiting each other. By tracking their dance for decades, astronomers Russell Hulse and Joseph Taylor found that their orbit was decaying exactly as predicted by Einstein, energy being carried away by ripples in spacetime. This was the first indirect but brilliant confirmation of gravitational waves, years before LIGO direct detection. These stars are not perfectly smooth spheres. Their crusts, a crystalline lattice of iron nuclei, can crack under immense strain, releasing energy in starquakes that momentarily change the pulsar's spin. What happens when gravity compresses matter beyond the atomic scale? We find a state of existence governed by a single, elegant equation, a boundary where matter is pushed to its absolute limit before vanishing from our universe entirely, hidden behind the cosmic censorship of a black hole's event horizon. A singularity exposed to the universe would be a tear in the fabric of reality, a point of infinite density where the known laws of physics cease to function. The cosmic censorship hypothesis, proposed by the renowned physicist Roger Penrose, is a bold conjecture that nature forbids such a spectacle. It argues that gravity always wraps its most destructive singularities in the protective shroud of an event horizon, creating a black hole that hides the infinite from view. This is the 19th astonishing defiance, the idea that gravity polices itself to preserve cosmic order. The principle is crucial for maintaining predictability in our universe. If a naked singularity, one without an event horizon, could exist, then anything could emerge from it. The cause and effect we rely on would break down completely, and we could no longer predict the future evolution of any system near it. It is a cosmic safety mechanism, ensuring that the unseeable chaos at a singularity's heart remains locked away, unable to influence the outside cosmos. Yet, like any good rule, physicists have searched for exceptions. Through complex numerical simulations of collapsing stars and theoretical explorations of high-energy collisions, potential counterexamples have emerged. Certain solutions within Einstein-Maxwell theory, which describes how gravity interacts with electromagnetic fields, appear to permit naked singularities under very specific, fine-tuned conditions. Experts like Kip Thorne have debated whether these are mathematical curiosities or genuine threats to the conjecture. The hypothesis is deeply intertwined with black hole thermodynamics and the ongoing puzzle of information loss. If information truly vanishes into a singularity, its naked exposure would make that loss a public and paradoxical event. By keeping the singularity censored, gravity may be enforcing a deeper law about how information is preserved, even if we cannot yet see the mechanism. Why would the universe go to such lengths to hide its own deepest secrets? This self-concealment suggests that gravity's rule over spacetime is not absolute, but comes with a fundamental limitation, a need to shield the rest of reality from its own destructive core. This act of cosmic censorship reveals a universe that, for all its violence, maintains a fragile order by keeping its ultimate mysteries locked away. A final defense against the chaos that lies at gravity's heart. Even the most fundamental constants of nature may not be eternal. The 20th astonishing defiance is the radical possibility that the strength of gravity itself could be changing over time. This idea that the gravitational constant, big G, might be slowly weakening as the universe expands, directly challenges the bedrock of Einstein's general relativity, which assumes its constancy. It was physicist Paul Dirac who first speculated on this in the 1930s, noticing curious numerical coincidences between the scale of the cosmos and the properties of subatomic particles. He wondered if these were not coincidences at all, but clues that the forces of nature evolved together. If true, the consequences would ripple through everything. The orbits of planets would gradually widen, the energy output of stars would subtly shift, and our entire cosmic history would need to be rewritten. Pioneers like Arthur Eddington immediately began testing this, seeking any sign of drift in the motions of the moon and planets. For decades, the results came back negative. Today, we have exquisitely precise tools to hunt for this variation. Lunar laser ranging experiments fire beams at reflectors left on the moon by Apollo astronauts, timing the light's return to measure the Earth-Moon distance with millimeter accuracy. Pulsar timing observes the flawless clocks of spinning neutron stars for any tiny anomalies in their rhythmic pulses. Together, these methods have placed a tight leash on any potential change, showing that if big G is varying at all, it is by less than 1 part in 10 trillion each year. Yet the theoretical motivation persists. In alternative theories of gravity, like the Brans-Dicke scalar tensor theory, the strength of gravity is not a fixed number but a dynamic field, capable of evolving in space and time. Such frameworks often emerge naturally from attempts to unify gravity with the other forces, particularly in models involving extra-spatial dimensions. Here, what we perceive as gravity's strength could be diluted as these hidden dimensions stretch and evolve. This potential inconstancy might even offer a solution to modern cosmological headaches. The Hubble tension, the stubborn discrepancy in measurements of the universe's expansion rate, could potentially be resolved if gravity was stronger in the past, altering how we calculate cosmic distances and ages. Even the nature of dark energy could be reinterpreted, not as a mysterious vacuum energy, but as a side effect of gravity slowly fading away. What if the force that anchors our reality is itself a relic of a more potent past? This notion that gravity itself evolves with the cosmos leads to a final, breathtaking possibility. A reality where the laws of physics are not universal decrees, but local ordinances, varying from one bubble universe to the next in an infinite multiverse. Could the force that grounds us be nothing more than a local ordinance in a cosmos of infinite variation? This final astonishing defiance is the concept of the multiverse and its gravitational bubbles, a vision where the very laws of physics, including gravity's strength, are not universal decrees but random outcomes in an endless cosmic froth. This idea emerges naturally from the theory of eternal inflation, where the rapid expansion of the early universe never truly stops everywhere. Instead, new pocket universes continuously bud off, each a separate bubble with its own random set of physical constants. In the string theory landscape, another framework for the multiverse, there are perhaps 10 to the 500 possible stable configurations for the vacuum of space, each corresponding to a universe with different properties. Physicists like Max Tegmark have organized this dizzying prospect into levels, with a level 2 multiverse consisting of these isolated bubbles, each an entire universe beyond our cosmological horizon, forever separate and operating under its own unique rules. Within this vast ensemble, the strength of gravity is not a fundamental, unchanging number. It is a dial that was randomly set when our bubble universe formed. In another bubble, gravity might be so weak that matter never clumps into galaxies or stars. In yet another, it could be so crushingly strong that any star that forms burns out in a fleeting instant. This is where the anthropic principle enters the stage. It suggests that we find ourselves in a universe with a Goldilocks gravity, not because it is special or likely, but because it is one of the rare bubbles where the conditions are just right for galaxies, stars, planets, and ultimately, life to evolve. We could not exist in the vast majority of other bubbles where the constants are hostile to complex structure. How could we ever test such a radical idea? One potential signature might be etched into the oldest light we can see. If our bubble universe ever collided with a neighboring one in the distant past, the unimaginable energy of that impact could have left a faint, circular pattern in the cosmic microwave background, a bruise on the sky that astronomers have actively searched for. Could it be that our entire cosmic history, from the formation of atoms to the rise of life, is simply a consequence of a gravitational lottery win? This expansive view does not diminish the mystery of gravity, but magnifies it, framing our universe as a single, habitable island in an infinite ocean of possibility, where the force that shapes our reality is both profoundly local and eternally enigmatic. Newton's apple was more than a falling fruit. It was the first crack in a cosmic mystery. He envisioned gravity as a silent, instantaneous force reaching across the void, a mathematical pull that perfectly described the orbits of planets and the arc of a thrown ball. His law of universal gravitation, published in his Principia in 1687, was a triumph of human reason. Yet it contained a deep unease, a force that acted at a distance with no mechanism, no medium, no explanation for the how. For over 2 centuries, this was the accepted picture, a universe ticking along with predictable, clockwork precision. Then came Albert Einstein. He saw a flaw not in the math, but in the very idea of a force. What if gravity was not a pull, but a consequence of shape? His general theory of relativity, finalized in 1915, proposed a radical shift. Mass and energy did not exert a force, they told spacetime how to curve. And this curved spacetime told planets and light how to move. Objects were simply following the straightest possible path through a warped geometry. The proof came just 4 years later, during a total solar eclipse. As the moon blotted out the sun, stars near its darkened edge appeared slightly out of place, their light bent by the sun's gravitational field exactly as Einstein's equations predicted. This was the moment gravity transformed from a mysterious force into a property of space and time itself. This new understanding solved old puzzles, like the subtle wobble in Mercury's orbit that Newton's gravity could not fully explain. It was not a missing planet causing the anomaly, but the sun's mass gently twisting the fabric of space through which Mercury traveled. The mathematics evolved too, from Newton's calculus to the complex, tensor calculus needed to map the curvature of 4-dimensional spacetime. Later visionaries like Stephen Hawking pushed the boundaries even further, weaving quantum mechanics into the fabric of gravity. He discovered that black holes are not completely black, but slowly evaporate by emitting radiation, a quantum whisper at the event horizon. Each revolution in thought was built upon the last, each new theory not discarding the old, but encompassing it, showing that Newton's laws were a brilliant approximation of a deeper, more nuanced truth. How has our perception of this fundamental force evolved? It is a story of peeling back layers, each revealing a universe more strange and wondrous than the last. A journey that continues to this day as we seek to reconcile the cosmic curvature of Einstein with the quantum flicker of Hawking. From the cosmic scale of the multiverse down to the quantum realm, gravity consistently reveals itself as the universe's most profound and persistent enigma. This journey through its 21 astonishing defiances, from the invisible scaffolding of dark matter to the possibility of evolving physical laws, underscores a simple, humbling truth. We have mapped the warping of spacetime around black holes, felt the vibrations of colliding giants through gravitational waves, and puzzled over the repulsive force of dark energy blowing the cosmos apart. Each paradox, from Mercury's wandering orbit to the holographic principle, peels back a layer of reality, only to expose a deeper mystery beneath. These are not just problems for physicists to solve. They are invitations for all of us to look up and wonder, to question the very fabric of our existence. The force that grounds us to this planet is the same force that holds the key to understanding everything else. As Carl Sagan so beautifully reminds us somewhere, something incredible is waiting to be known. Let this exploration be your starting point. We would love to hear which gravitational wonder captivated you the most. Share your thoughts in the comments and subscribe to continue unraveling the cosmos, one gravitational mystery at a time.